Hi everyone, my name is Caio, and I'm glad to be here presenting our project Characterization of Implied Scenarios as Families of Common Behavior. So our plan for today is give some introduction, why we did this work, then the background, present our methodology, what results we got throughout our experiments, and discuss them at the end. So let's get started. So implied scenarios are unexpected behaviors. So these are scenarios that we didn't plan for them to happen, but they can still happen at runtime. However, detecting these scenarios is a decidable problem. Our methodology reduces the problem space by allowing the user to resolve multiple implied scenarios together. Existing literature before our work only allowed the user to resolve implied scenarios one by one, and our methodology reduces this problem space by grouping them in a meaningful way. The figure here shows emergent behavior happening in real life. So that in a train crossing, the blockades went down and the cars started lining up. Over an hour went by without no trains actually being there. So something wasn't planned, the cars waiting for nothing, but actually happened. So onto our background. So let's start with scenarios. So a scenario depicts a system action. So it shows, in this case, which components are talking to which other component, the order these interactions happen, and in which order these scenarios can happen. So in a single scenario like this one, we can have multiple interactions, and the order in which each scenario can happen is this one. This specification is of the boiler system, which we're going to use as an example throughout our presentation. It consists of 4 components that work together to keep the pressure inside of a boiler between certain thresholds. It can start at initialize. It has to start initialize by turning on. Then it measures the current pressure, and after that, it can start having choices. And then it just starts over again. So given this specification, we can check our first implied scenario. So this scenario on figure 3 is an unexpected scenario that we did not model in the specification. However, it can happen at runtime. So right after turning on, right here, the system queries the last pressure measured. However, that pressure can be very old because the system was turned off. A lot of time could have passed between the system turning on again, and we don't want the system to act on old information. So this is an unexpected behavior that happens because each component believes it's acting properly, but the global behavior, it's not actually okay. The last piece of background we need is the Smith-Waterman algorithm. This is widely used in bioinformatics to find alignments between genetic sequences. In our framework, in our methodology, we're going to use this algorithm to align message sequences. So for this example, we can see that between these 2 sequences, the one on the top and the one going down on the left, this is the best local alignment. The dash represents a gap, so saying something should be here, but it's not, so let's just say something would match the C from the other sequence. And it gives us a score of how good this alignment was, or how similar these sequences are. Now, with background out of the way, let's get on to our methodology. So this is an overview of our methodology. It has 6 steps. First, the user would model the system scenarios, like the boiler system we saw on the background. After that, we're going to build the architecture model, which means that we're going to take all those scenarios and see all the possible behaviors the system could have at runtime. And we'll detect implied scenarios, so behaviors we did not model but are actually happening in the architecture model. If there's no implied scenarios, good to go. We don't have to do anything else. However, if there are implied scenarios, then we're going to try to find common behaviors. So we're trying to find the cause among different implied scenarios, so something that's similar to all of those. After we have these common behaviors, we're actually going to try to group them again. So now we're going to try to find a meaningful classification of families of common behaviors. So we're going to try to find these root causes of implied scenarios, and now we're trying to find similarities between these root causes. If the family of common behaviors is wanted, we missed something on the modeling. So it's some acceptable behavior that we just forgot to include. If it is not wanted, we're going to create a behavior constraint. So something that goes on top of our architecture model that's saying, hey, you cannot actually do that. Or after doing this, you must do that. This will prevent our system from executing something that we did not want. And we keep doing this classification and creating constraints while we still have unresolved common behaviors. After we don't have any unresolved common behaviors, we're going to build a new constraint architecture model by taking the original architecture model that has all the possible behaviors, including the unwanted ones, and putting the constraints on top of them. So we're going to restrain the possible outcome of the system and only accept what we actually want. Our focus of our contribution is steps 3, 4, 5. There's already literature work on the other steps, so we chose to focus our contribution on this literature gap. And that's where we're going to take a closer look into this presentation. So let's start with step 3. So as a proof of concept, we use the tool LTSA-MSC to detect implied scenarios. This tool detects implied scenarios as error traces, which means it's a sequence of messages, and the last message is the one that caused an error. So we assume that whenever a message is repeated, the system is going to a same abstract non-error state. So on the previous implied scenarios we saw, when we see the on message and the second on message, we're assuming that both on messages are taking the system to a same state. Doing this, we can remove loops of messages and find the unique behavior of each scenario. So here on figure 8a and 8b, we have two examples of implied scenarios. The first one is the one we saw earlier. The second one is similar. It only has a second pressure message. By removing the loops on repeated messages, so when we see two on messages, we remove everything that happened between them, we find this common behavior on query, which is the same for both scenarios and explains what's going wrong with both scenarios. Right after turning on, the system is querying without checking the current pressure. After we have these common behaviors, we're going to try to find families of common behaviors. So how do we do that? We actually use the Smithman Algorithm to find the alignment of different common behaviors, and also we use the score, or rather the inverse of the score, to find how different these common behaviors are. We use this as a distance function. So if this Smith-Waterman score was very high, the inverse, or the dissimilarity between two common behaviors, is going to be very low, and we can use this as a distance metric when we're grouping our common behaviors. For the boiler system on this figure, we're showing the two and only two detected common behaviors for the system: on query on top and on pressure query data comment off going down on the left. The best alignment for these two common behaviors is this one, on gap query, on pressure query. This shows the user who has the domain expertise that these are not actually similar, because the second common behavior has a pressure where the first common behavior does not, and the lack of this pressure message is the cause of that common behavior. So these two are separate families of common behaviors. After we have defined these families, how can we constrain them? So we're going to create constraints that remove all implied scenarios of the family. So here, as an example for the boiler system, we create a constraint that says whenever we see a message on, we need to see a message pressure after it. So after someone sends an on message, we disallow query from occurring. And this would remove all the different variations of that implied scenario that are part of the same common behavior. So this would remove multiple implied scenarios by constraining a single behavior of the system. So on to our results. So we did 7 case studies from system specifications found in the literature. And for each one of them, we tried to collect up to 500 implied scenarios. So remember that the detection problem is undecidable. So we needed this upper threshold so we could stop. And as a proof of concept, we treated all implied scenarios as negative. So we said everything unexpected is unwanted. Because our focus was not to remodel the system, we're just including more behavior constraints to remove these implied scenarios. So here is an overview of our results. So we did these 7 case studies. Interesting thing here is that for 3 of them, APTS, SSMOS, and the SmartCam, we actually have very few implied scenarios. So our tool stopped collecting implied scenarios because it collected all of them. However, for the other ones, for the boiler and for the cruiser, we actually hit our threshold of 500. For EB2B and for GSM, the tool actually crashed because the implied scenarios were getting so long that you ran out of memory to keep collecting. Because it's an undecidable problem, again, we're not sure if there was more or there were not, but we said these were enough to do our analysis. Across all 7 case studies, we collected just shy of 1,800 implied scenarios. To collect all these scenarios, we demanded nearly 37 hours just collecting them. After this collection time, applying all automated process of our methodology, so detecting the common behaviors, applying the Smith-Waterman algorithm, and producing all files that can guide the user, across the 7 case studies took 3 seconds. So it's a very small overhead when we compare it with the 37 hours that we spent collecting implied scenarios. By doing this automatic analysis, we're able to go from 1,800 implied scenarios down to 81 common behaviors. So just automatically, we're able to reduce a lot of the elements the user needs to check. By giving the user with the extra information to group even more these common behaviors, we're able to manually find 14 families of common behaviors, or we're able to resolve all common behaviors and all implied scenarios by creating 14 constraints. So we went down from 1,800 implied scenarios to 14 families of common behaviors, and each one of them requires one constraint, so we resolved everything with 14 fixes. As an example for one of the case studies, here we actually had 16 common behaviors. You can see on figure A how our Smith-Waterman distance actually gives the user a good view that this potentially has 2 separate families, as the group on the left has a much higher distance from the group on the right. However, with further manual analysis, we actually saw that all these 16 common behaviors were actually resolvable by a single constraint. So they had the same cause and thus were part of the same family of common behaviors. So for the GSM system, we collected over 300 implied scenarios and were able to resolve all of them with a single constraint. Another analysis we did is we checked how many common behaviors were detected by how many implied scenarios were collected. So here we see that at 100 implied scenarios, we collected the most common behaviors for all systems. So after 100 implied scenarios, we will not gain any new information for the analysis we did with our methodology. So this could save time when collecting implied scenarios, because we don't have to go up to 500, we could actually stop at 100. Finally, lastly, all system specifications had their reliability increased to 100% after we applied our methodology. We used the reliability calculation by Rodrigues et al., where we check how often does the system get to an accepted end state. After we add our constraints, all 7 case studies always reach an acceptable end state. So this is how we get to 100% reliability. So to summarize, we propose a methodology that reduced 1,800 implied scenarios to 14 families of common behaviors. This equals to 0.7% of the original elements, so reduces by a lot the number of manual analysis the user needs to do. In hindsight, we would be able to stop the collection of implied scenarios much earlier, so this would also save some time. And finally, all 7 case studies had their reliability increased to 100%. This is the related work at the time of our publication. Almost all of them only focus on detection of implied scenarios. The few of them that actually suggest solutions do not restrict the problem space, and that's where we focused our contribution. For future work, we'd like to detect automatically when the implied scenario collection can be stopped. We'd like to automatically reason about the implied scenarios, which would allow us to generate constraints automatically. And we also want to check how multi-sequence alignment instead of pairwise alignment can help this problem. Thank you for your time, and I'm glad to answer any questions you have. Thanks.